This lab is going to try to illustrate the relationship between torques applied to an object and the corresponding rotational acceleration based on the inertia of the object. Our textbook defines torque as a product of force and lever arm that the force is applied in order to make an object rotate. The lever arm is the perpendicular distance from the center of rotation of an object to a point where the force is applied. Rotational acceleration is the change in rotational velocity with time. Something like linear acceleration is the change in linear velocity with time. The inertia of a body is its resistance to its change in motion. For extended bodies like spheres and cylinders, this can be related to the object's mass and size. When you go to the site, use the check boxes to choose one of 4 different objects: a solid sphere, a hollow sphere, a solid cylinder, and a hollow cylinder. Put your object choice on the data table. You can use the radius and mass sliders to set initial values that you want for your object. Record these in the data table. If you slide the force slider, you will see different torque values listed. If you choose a force and hit the start button, the object will begin to rotate and you will see a value show up for rotational acceleration. Hit the pause button and reset button to do a new run after recording your torque and rotational acceleration values. Make sure your mass and radius values do not change when you hit the reset button. You will choose 10 different randomly picked values for the force between 10 and 50. You should spread it out over the full range just to get an idea. For each new force, write down the torque and the corresponding rotational acceleration to complete Table 1. For Part 2, you want to see how mass and angular acceleration are related. So you will keep your same object, fix its radius, and fix the force. To get data, vary your mass through 10 values while recording angular acceleration when you hit the start button. Once you have filled data 2 with mass and angular acceleration values, making sure to span the potential range of mass over its extremes, you're ready for Part 3. For Part 3, you want to see how radius and angular acceleration are related. You will keep your same object, fix its mass to the value you kept constant in Part 1, fix the force to the value that you kept constant in Part 2, and choose 10 different radius values. For each new radius, hit the start button and get the corresponding torque and angular acceleration values. Again, choose the radius to range over the extremes available in the simulation. Once Table 3 is filled, you're done collecting data. Minimally, it would seem that you will complete 3 graphs. But as has been done before, if you do not end up with a linear graph, then you will need to linearize it. Equations found in Chapter 8 can help you decide what you will need to do to linearize any non-linear graph. Changing the power of a variable, either to get a reciprocal of that variable for graphing, or squaring that variable for graphing, or some other power of variable for graphing, and getting a linear graph. In all 3 graphs or more, you want angular acceleration on the horizontal or x-axis. On the vertical will be torque, mass, or radius, or some power applied to them as needed. Looking at the torque equation and putting into it the expression for the inertia of your chosen object can help with this. It will also help you determine what all makes up the slope, how those items you kept constant appear in the torque equation when you have manipulated to match what you have graphed on the vertical and horizontal axes. And as usual, all fits the data that tend toward the y-axis should be projected to the y-intercept. What you will submit in your Word document lab write-up. In addition to answering the questions and providing completed data tables, there will be between 3 and 5 graphs that need to be properly done and appear on their own pages, filling that page. So, proper title for the graph, proper axes labels, a line fit to the data, extended to the y-axis if it need be, and if you use Excel, an equation for that fitted line on each graph. And you should have a calculations page that includes each of the calculations specified in the analysis section of the write-up.